I'm Herb Gross, and welcome once again to Gateways to Algebra, lecture number 7, where we're going to be talking about the arithmetic involving whole number exponents. See, again, like everything else, once we define the concept, we have to talk about how to build with it. But some interesting things start to happen almost instantly. For example, what did we do last time? We talked about 2 to the 4th power, didn't we? And that meant what? 2 times, let's just do it, 2 times 2 times 2 times 2. And what would 2 to the 3rd power mean? 2 to the 3rd power would mean 2 times 2 times 2. Now suppose I wanted to combine these two by adding them. See, I'd say 2 to the 4th power plus 2 to the 3rd power. Can you see people who are memorizing just sort of saying things like, oh, this is an addition problem, so I'll just add the 4 and the 3 and call that 7. Well, you can say things like that, but remember, once you've made up a definition, you have to live by it. You can make up whatever definitions you want, but once you make them up, you have to abide by them. 2 to the 4th power is another name for what? 2 times 2 times 2 times 2. That's another name for 16, isn't it? See, 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 to the 3rd power is 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. So the problem really says what? 16 plus 8, which happens to be what? 24. Now, you could say, hey, I think that we should say 2 and 2 is 4, and 4 plus 3 is 7. So this is a free country. I can do it my way. He can do it his way. I'm going to call the answer 4 to the 7th power. Well, you can call it 4 to the 7th power, but look what you're saying. 4 to the 7th power is multiplying 7 fours together. 4 times 4 is 16, times 4 is 64. Heck, we're already way bigger than the correct answer, and we got all these 4s to multiply by yet. You say, well, I don't care. Well, you have to care, because once you've accepted this definition, 2 to the 4th means 16. 2 to the 3rd means 8. And 2 to the 4th plus 2 to the 3rd means 16 plus 8. And whatever you do, since 16 plus 8 is 24, any rule that you make up for doing this problem had better give you 24 for the answer. By the way, if you want to see why this idea of adding the 4 and the 3 doesn't work, notice that even though you have 7 2's here altogether, they're interrupted by a plus sign. See, and what happens is what? Remember what we said? In mathematics, multiplications are done before additions. We have to do what? Multiply these 4 2's together and then multiply these 3 2's together before we add them. Look what a different thing would have happened if that plus sign had been a time sign. Watch the same logic now. 2 to the 4th power means 16, doesn't it? 2 to the 3rd power is still 8. 16 times 8 is 128. Now let's see what we can do over here. 2 to the 4th power still means 2 times 2 times 2 times 2. 2 to the 3rd power still means 2 times 2 times 2. But now there's a time sign in here, isn't there? Okay? Put a time sign here, and what's happening? These 4 factors of 2 are being multiplied by these 3 factors of 2. In a pure multiplication problem, you don't need the parentheses. What do you have altogether over here? A string of 7 factors of 2. The answer to this problem is 2 to the 7th power. And let's figure it out. 2, 4, 8, 16, 32, 64, okay, 128. 7 2's multiplied together gives you 128. See, this is the correct answer. And what did you wind up doing over here? You kept the common base and added the exponents. It almost sounds like part of that rule for adding fractions. See, for fractions you need what? A common denomination, and you add the enumerations. Here we're saying what? When you're multiplying 2 numbers with the same base, you keep the common base and you add the exponents. And can you see why that's happening over here? And by the way, you might say, well, why do you write 2 to the 7th over here? I understand what 128 is. No, the 2 to the 7th tells you where it comes from. Let me see if I can give you a different example. This is one I always have, I like to explain to people because it has a lot to do with common denominators. I say, what is 3 times 4? The average person says 12. That happens to be a true statement, but there's a better way of visualizing this. 3 times 4 is the third multiple of 4. It's the third number you come to when you're counting by 4s. See, 4, 8, 12. It's also the fourth number you come to when you're counting by 3s. See, 3, 6, 9, 12. See, 3 times 4 equals 12 gives you a numerical answer. This tells you what's important about that number. For example, suppose you don't have a calculator, and I say, within 10 seconds, tell me what is 123 times 89. No calculator, nothing. It's what? It's the 89th number we come to when we're counting by 123s, and the 123rd number we come to when we're counting by 89s. It happens another name for this number is 10,947, and that would be the common denominator in a problem where one denominator was 123 and the other denominator was 89. You see, it would take a long time to find a common denomination for 89 and 123 just by listing the multiples of 89 and listing the multiples of 123. But you see, this tells you exactly what is meant. But anyway, let's see if we can summarize the first rule. The first rule says if b is any number and m and n are any positive integers, the positive integers are the numbers we use for counting, 1, 2, 3, 4, 5, etc. Then it says what? b to the m times b to the n. What's the rule? Keep the common base and add the 2 exponents. In other words, if somebody says to me, how much is 3 to the 5th times 3 to the 4th, even though there's a time sign here, what do? I keep the common base, which is 3, and add the 2 exponents, which is 9. And rather than memorize this, let me always think back to the definition so I can see what's happening. 3 to the 5th power means what? 3 times 3 times 3 times 3 times 3. That's 5 factors of 3, isn't it? 3 to the 4th power means 3 times 3 times 3 times 3. That's 4 factors of 3. How many factors of 3 do I have altogether? You see, because this is a multiplication sign, it allows me to add all of these because this string of 5 factors is connected to this string of 4 factors by the time sign. See, 5 3's here, 4 more here is 9. Altogether, I'm doing what? Multiplying 9 3's together. You see, again, let's just pause briefly so that I can make sure you understand this. It's like a person saying to somebody, is the water warm? And the guy says yes. So he jumps in and he almost freezes. He says to the guy, I thought you said the water was warm. He says, gee, it looked warm. You see, it looks like you can do certain things, but we always have to do what in logic? Once you make up your definitions, you are responsible for what those definitions imply. For example, I can make up how many inches there are in a foot. I say, okay, there's going to be 12 inches in the foot. I could have said 13, I could have said 15, but I made it 12. I also decided to put 3 feet in the yard. That's arbitrary. It could have been 2, it could have been 4. But once there are 12 inches in the foot and 3 feet in the yard, I have no choice as to how many inches there are going to be in the yard. 12 times 3 is 36. Therefore, there has to be what? 36 inches in the yard. I do not have the right to say there will be 12 inches in the foot, 3 feet in the yard, and 47 inches in the yard. It would be mathematically inconsistent. Okay? And by the way, the same kind of logic that works for multiplication has an inversion for division. In other words, when you multiply like bases, you add the exponents. Can you guess what's going to happen when you divide like bases? Well, why guess? Let's take a look. Well, we won't take a look. There we go. Suppose I have 2 to the 7th power divided by 2 to the 3rd power. Okay? That means what? 2 to the 7th, divided means over in the language of fractions, 2 to the 3rd. Let me not do any guessing at all. Let me just write out what the definition says. 2 to the 7th power means what? 2 times 2 times 2 times 2 times 2 times 2 times 2. 7 times. 2 to the 3rd power means 2 times 2 times 2. Now remember, this course is a sequel to arithmetic. I assume you remember arithmetic and consequently how to reduce fractions. Can't we cancel a common factor every time it appears in both the numerator and the denominator? See, one of the 2's here cancels with one of the 2's here. One of the 2's here cancels with another 2 here. And the third 2 here cancels with the third 2 here. Now I have no more 2's to cancel. How many 2's did I start with altogether? I started with 7, didn't I? How many did I cancel out? 1, 2, 3. In other words, I started with what? 7 2's and canceled out 3 of them. I have 7, crossed out 3. You see what happened over here? To divide this problem, what did I do? It was the same base. I kept the common base, and I did what? I subtracted the exponents. 7 minus 3. Another way of writing this would be what? 2 to the 4th power. Don't say 3 doesn't go into 7, so I don't know how to do this problem. You don't have to divide 3 into 7. What you're really saying is what? The 3 factors of 2 in the divisor cancel 3 of the 7 factors in the dividend to leave me 4 factors of 2 in the quotient. See, again, let me warn you. If you have 2 to the 6th power divided by 2 to the 3rd power, don't say 6 divided by 3 is 2. Don't say 2 divided by 2 is 1. 2 to the 6th power divided by 2 to the 3rd power is what? 2 to the 3rd power. How do we know that? Well, 2 to the 6th power means 2 times 2 times 2 times 2 times 2 times 2. 2 to the 3rd power means 2 times 2 times 2. There are 6 factors of 2 upstairs. There are what? 3 factors of 2 downstairs. The 3 factors downstairs cancel with 3 of the 6 upstairs, leaving me with 3 factors. 2 to the 3rd power happens to be 2 times 2 times 2, which is 8. And now let's check to see whether this works or not. 2 to the 6th power is 2, 4, 8, 16, 32, 64. 2 to the 3rd power is 2, 4, 8. 2 to the 6th divided by 2 to the 3rd is 64 divided by 8, and that answer is 8, which happens to agree with 2 to the 3rd. 2 to the 2nd only happens to be 4. So no matter how logical this looks, it doesn't count unless it follows from the definition. And let's generalize that. To generalize it, we say what? If you're dividing like bases, you subtract the exponents. B to the mth power divided by b to the nth power is b to the m minus n power. And we assume that m is greater than n because, after all, we've only talked about whole number exponents, and if m is less than n, you're going to have a negative exponent. Of course, we'll deal with that later, but let's just take a look at this for the time being. Suppose, see, all this says is what? B can be any base, m and n can be any whole numbers as long as m is more than n. So I pick b to be 5, m to be 3, and n to be 2 over here. So this says what? 5 to the 3rd power divided by 5 to the 2nd power is 5 to the 3 minus 2 power. 3 minus 2 is 1, so it says what? 5 to the 3rd power divided by 5 to the 2nd power is 1 factor of 5, which is 5. And to check this out, 5 times 5 is 25, times 5 is 125. 125 divided by 25 is 5. And if you want to see this in terms of how we get this rule, 5 to the 3rd power is 5 times 5 times 5. 5 to the 2nd power is 5 times 5. The 2 factors of 5 downstairs cancel with 2 of the 3 factors of 5 upstairs, leaving you with 1 factor of 5, or 5. Now, by the way, this worked okay if m was bigger than n. But suppose now m is 2 and n is 3. This would say what? 5 to the 2nd power divided by 5 to the 3rd power is equal to 5 to the 2 minus 3 power. 2 minus 3 is negative 1. And by the way, notice that if we hadn't invented negative numbers before we got to exponents, we'd have to do it now. Because look what happens. We suddenly have an exponent that doesn't make sense. Because how can you multiply something by itself negative 1 times? So you can multiply it by itself once, or twice, or 3 times, but not negative 1 times. And again, let me show you how logic works. If we want b to the m divided by b to the n to still be b to the m minus n, even when m is smaller than n, then b to the negative 1 must, not should, but must mean the same thing as 1 over b. In other words, you take the minus sign out, and all the minus sign tells you is what? Take the reciprocal. Now, why is this? Don't memorize it, just try it. Suppose you want 5 to the 2nd power divided by 5 to the 3rd power to be solvable by using this rule. We would take what? The base is 5, and you subtract what? The 2nd exponent from the 1st, so the answer would have to be what? 5 to the 2 minus 3. But we know that 2 minus 3 is negative 1. Therefore, the answer to this problem would have to be 5 to the negative 1. Now, that's awkward because we don't know what that means. But could we compute this a different way? We know that 5 to the 2nd power is 5 times 5. We know that 5 to the third power is 5 times 5 times 5. In fact, isn't this just the reciprocal of 5 to the third divided by 5 to the second? Now what happens is what? The 3 factors of 5 are downstairs rather than upstairs. Can I still cancel 2 of the 3 factors downstairs with both factors that are upstairs? Remember, every time you cancel, there's a 1 left. So what's left on top? 1 times 1 is 1. What's left on the bottom? 1 times 1 is 1, times 5 is 5. We're left with 1/5. Well, if this has to be 1/5, but by using this rule, it has to be 5 to the negative 1, and there's only one answer to the problem, this must be 2 different names for the same number. 1 to the 5th has to equal 5 to the negative 1. It's sort of like saying if only one person wrote Huckleberry Finn, and you read that it was written by Mark Twain, and someplace else you read it was written by Samuel Clemens, and only one person wrote Huckleberry Finn, how can that happen unless Mark Twain and Samuel Clemens are just 2 different names for the same person? That's what we do a lot in mathematics. See, let's try another example that way. Suppose I had 5 to the third divided by 5 to the 7th. If I want to use that rule, it's what? 5 to the 3 minus 7. But 3 minus 7 is negative 4. Okay? Well, 5 to the third we know means 5 times 5 times 5. We're dividing, that means over 7 factors of 5. Now, can't I cancel each factor of 5 from the numerator with a factor of 5 from the denominator? If I do that, I finally cancel out what? 3 of the 5s on the top, okay, with what? 3 of the factors of 5 on the bottom. That still leaves me with what? It still leaves me with 4 factors of 5, but they're on the bottom, and on the top is what? A 1. So 5 to the negative 4 says what? The first thing you do is pretend the negative sign wasn't there and write 5 to the 4th, and then the way you replace the negative sign is you make it the reciprocal. See, in other words, b to the negative n is the same as what? 1 over b to the n. And again, as the course goes on, we're going to do more and more of this. But let me show you how this works with place value. We saw before that multiplying by 10 to the 5th means we move the decimal point 5 places to the right. In other words, here's 7.1. We're multiplying by 10 5 times. Every time we multiply by 10, we move the decimal point 1 place. Well, there's only 1 digit, so to move it 5 places, we need 4 zeros. 1, 2, 3, 4. 7.1 times 10 to the 5th is what? 710,000. You see, in other words, when you're multiplying by a power of 10, the magnitude of the exponent tells you how many places to move the decimal point. I claim the sign is going to tell you in what direction to move it. See, 7.1 times 10 to the 5th meant move the decimal point 5 places to the right. I claim that 7.1 times 10 to the negative 5 is simply going to say what? Move the decimal point still 5 places, but now in what direction? To the left. Now, how can I prove that? Let's go back to our definition. 10 to the negative 5 means 1 over 10 to the 5th. Okay? Multiplying by 1 over 10 to the 5th is the same as dividing by 10 to the 5th. Every time you divide by 10, you move the decimal point 1 place to the left. Since I'm dividing by 5 factors of 10, I've got to move the decimal point what? 5 places to the left. And since there's only 1 digit to the left of the decimal point, I've got to annex 4 more zeros, 1, 2, 3, 4. And so the answer is what? 0.000071. And notice how much more efficient, once you get used to it, this is over trying to read this. By the way, just one more thing to point out to show you how this rule works. Suppose I want b to the m divided by b to the n to be b to the m minus n. Okay? I want that to be true even when m equals n. Then I claim that b to the 0 has to be 1. Well, see, let's see why. Suppose I take 3 to the 5th and I divide it by 3 to the 5th. Using this rule, isn't that 3 to the 5 minus 5? But 5 minus 5 is 0. So 3 to the 5th divided by 3 to the 5th has to be 3 to the 0. On the other hand, except for 0, because 0 over 0 is undefined, what happens when you divide any number by itself? You always get 1. Well, if the answer to this problem has to be 1, it also has to be 3 to the 0, and there's only one answer. It must be that 3 to the 0 equals 1. Okay? Let's see if we can find some more rules. See? Remember we said that when you take 2 to the 5th times 2 to the 3rd, one of the problems that you have over here is people say, oh, this is a multiplication, so I'll multiply the 5 times the 3. Well, the answer to this problem isn't 2 to the 15th. It's equal to 2 to the 8th, isn't it? You have 5 factors of 2 and 3 more factors of 2. That's 8 factors of 2. However, there is a problem to which 2 to the 15th would be the right answer. Suppose I took 2 to the 5th and raised that to the 3rd power. See, anything raised to the 3rd power means the thing times itself times itself. So if I put 2 to the 5th in here, 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 how many factors of 2 do I have in each set of parentheses? I have 5 factors of 2 in each set of parentheses. Therefore, how many factors of 2 do I have altogether? 5 here, strung together with 5 here, strung together with 5 here. Isn't that going to be 15 factors of 2 altogether? In other words, if you raise a power to a power, then you multiply the exponents. See, if you take 10 to the 12th power and then raise that in turn to the 2nd power, that will give you what? 10 to the 24th power. You multiply the 12 times the 2. Do you see why? Because raising to the 2nd power means to multiply the thing by itself. And if I multiply this by itself, I'm getting what? 10 factors of 2 and 10 more factors of 2, and that's going to be what? By our previous rule. And again, you have to be careful. Up until now, we've been dealing with the case where the bases were the same, but the exponents were different. Now, here's an example where the bases are different, but the exponents are the same. And the guy says, my gosh, what am I going to do now? And the answer is, don't worry about it. Whenever you're given a problem and you know the basic definitions, go back to them. What does 2 to the 4th power mean? It means 2 times 2 times 2 times 2. What does 3 to the 4th power mean? 3 times 3 times 3 times 3. Aren't there just as many 2's as there are 3's? And in a pure multiplication problem, can't we regroup and order any way we want? Why not write this as 2 times 2 times 2 times 2, and then put the 3's underneath, times 3 times 3 times 3 times 3, to emphasize that each 2 bonds with a 3 to make a 6. See, 2 times 3 is 6, 2 times 3 is 6, 2 times 3 is 6, 2 times 3 is 6. So what do I have for the final answer? The base is 6, which just happens to be what? 2 times 3, and the exponent is 4. In other words, when the bases are different and the exponents are the same, what do? You actually multiply the exponents, but you keep the base the same. And again, if you're memorizing, do you see how easy it would be to confuse these problems? See, here you do what? Keep the common base and add the exponents. Here, you multiply the 2 bases and you keep the common exponent. Isn't that kind of confusing if you're memorizing? You see what I'm saying? Let me just show you, as we're talking about this, again, what am I emphasizing? Never rely on memory. Do the thing logically. And after you've done it enough times, you will by default have memorized what's supposed to happen because you'll have used it so many times. When a boxer gets hit in a boxing match and they want to see if he's okay, they don't say, what's Einstein's theory of relativity? They say, what's your name? Because your name is such second nature to you, it's going to take a lot to make you forget that. The more second nature something is, the less chance there is you're going to forget it. Students say to me, I froze on the test. I forgot every single thing. I said, did you forget where you were? Did you forget your name? No, you don't forget every single thing. You forget the things you're not sure of. And what's the best way to be sure? Go slowly. Go back to the basic definitions. Sometimes something won't match anything. Here, let's just close on this example. Here's a case where neither the bases nor the exponents are alike. What are you going to do here? Well, I don't know. You do know what? That 2 to the 3rd power means 2 times 2 times 2. 5 to the 4th power means what? 5 times 5 times 5 times 5. Every time I can match a 5 with a 2, I get a 10. So here's a 2 times a 5 gives me 10. 2 times 5 gives me 10. 2 times 5 gives me 10. And there's still one 5 left over. So evidently, the answer to this problem is what? There's a 5 multiplied by 3 factors of 10. Person looks at me and says, I don't know how you got from here to here. I can't see the pattern. Well, I can't see the pattern either. All I know is what? This is the basic definition. If If this is the problem, this must be true. If this is true, this is true. If this is true, this is true. And therefore, this is the answer, whether I understand it logically, simply or not. I don't have to understand this stuff intuitively. And I think this is a good place to stop for today, because I think it's very important that you look over these rules for exponents. And again, I'm keeping away from algebra proper so far, so all these new topics can sink in. And probably within a few more lessons, we'll get back to using all this stuff as we come back to answer the question we asked after the very first lecture that said, if algebra is this simple, how come it's taking so long to do it? How come it takes so many years to learn algebra? And I want to show you where all these nuances come up. But let's take it one day at a time. So keep studying, have fun, stay young.